have to continue to the next presentation. And the next presentation will be by Leon Marshall, and he will tell us about climate and land use change impacts on bumblebees.
Okay.
Leon.
Yes, hello everyone. Talking into the void, it seems a bit, but I hope everyone's out there listening. I hope everyone's having a nice weekend. And I'm a postdoc researcher at the University of Libre de Bruxelles in Belgium. And I will talk today about my work trying to understand the role that climate change and land use change has on bee distributions. Is that changing the slides? Yes, there we go. So the other talkers have done a nice job showing how complex the relationship that bumblebees have with the environment is. And I'm going to come along and ruin that a little bit and say, can we simplify this in a way to make meaningful future predictions of bumblebees under global change, under climate change, under land use change? And so these are commonly used in ecology to look at future scenarios of how biodiversity may be affected by changes in climate, changes in land use. And these tools are only as good as the data that goes into them. So what I'm going to show today is break it up into two parts. The first part is looking at work that we've already done on using land use changes alongside climate changes to predict bumblebee distributions, but then also some other studies I've involved in from the past that show us that maybe there's more information we could be trying to get into these models to make them more useful. And that's particularly related to two projects, which I will briefly talk about, which is one related to trait plasticity and adaptability and species interactions. So in the broadest sense, what am I talking about when I talk about the impacts of climate change and land use change on bumblebees? And so really that's potential future increases in temperature, increases in extreme weather events, alongside long-term changes to natural habitats that are converted into intensive agriculture, into urbanization, and that can lead to loss of suitable habitat, so feeding and nesting resources for bumblebees, which in turn is likely to drive either distributional shifts, so bumblebees chasing the suitable climate conditions over a long time period, or adaptation to these new conditions. And so where did we start with this research? So we built upon the fantastic work of Resmont et al. With the Climate Risk Atlas of European bumblebees, which looked at the projections of bumblebees in Europe under future climate change scenarios, ranging from a sustainable scenario, a scenario where the temperature increases and extreme weather events are related to business as usual, or a scenario where really unregulated growth is the future that we may have for ourselves. And under all but maybe the best case scenario, there is strong regressions predicted for the majority of bumblebee species in Europe by 2100. But climate change is only going to be one aspect that's driving the decline of bumblebees. And so if I talk about this figure here from Urban et al., published in Science in 2016, they really summarize how much extra information we need to make meaningful predictions in the future about biodiversity distributions. And that is no different for bumblebees. I will come back to this figure later as we talk about some of the other aspects, but first we're focusing here, terrible at drawing. First we're focusing here on land use changes and environmental changes and how they're relevant. So as an example, we know that climate has not historically been the most important driver of bumblebee declines for certain species, and so we shouldn't assume that future distributions will only be driven by climate change. For example, if we take Bombus distinguendus, which has been extirpated from Belgium and the Netherlands and hasn't really been seen much since the 1970s and 80s, we know and can see that that's been driven by this long-tongued bumblebee losing moist flower-rich grasslands, and the loss of leguminous plants and leguminous crops, such as red clover. So the decrease in these, the change in this land use has probably led to the decline in this species. And so from a methodology point of view, I just want to sort of put it in context in the simplest way, how we can try and answer these questions about the future. So for example, for Europe, what we have and what we need is species observations. So basically any record of a bumblebee with coordinates, and we can apply that to environmental data. So in this case, climate data and land use data. And that we create a statistical relationship between the two. So create an estimation of at least the climate and land use niche of the species within this time period, within this equilibrium. And we can use that statistical relationship to project into the into different conditions. So these tools species distribution models can be used to look at areas that are undersampled to see potential diversity. They can be used to predict onto unknown areas to see the potential invasiveness of a species. Or in the case of the research I'm going to show you now, we can predict onto future conditions of climate change or land use change to see how habitat suitability or predictions of presence absence are likely to be affected by future scenarios. So for the research I'm going to show you now, we use very similar scenarios. Again, business as might be usual, an unregulated growth scenario, and a more sustainable scenario. So these are just predictions of how much the climate and the land use is going to change under socio-economic decisions made under these kind of scenarios. So to be able to do this, none of this work is doable without the many people collecting bumblebees, identifying bumblebees, curating collections, and maintaining databases. So firstly, thank you to all the people that do that. And so we're very lucky in Europe that we have a huge database over many years of bumblebee records across Europe. And you can see, though, the GIF's going a bit funny, but you can see that this has spatial and temporal resolution issues. So it's important that we understand how good the quality of the data is that's going in and make decisions about resolution and scale of which we can make meaningful models. So this figure as well has jumped a few years, unfortunately, so I might wait till it loops around. So this figure shows for each line is a bumblebee species. And we can see that over time, the rarer species have a pretty linear increase in the cumulative number of records. But you can start to see by the 1970s and the 1980s that how we collected bumblebees in the past is not how we're collecting bumblebees in the present. And you start to see a more exponential growth in the common species. And particularly that with citizen science improvements and the internet and the ability to identify common species quite easily, we see that there becomes quite a gap between the number of records we have for the common species and the number of records we have for the rare species. So it's important to keep this in mind when we're trying to build models about future distributions of bumblebees. And so you can see at the top, that blue line is Bombus bascorum, and you can see in the last 20, 30 years that really there's a huge number of records every year for that species. And this leads us on to important questions about scale and resolution. So if we want to meaningfully answer questions about where bumblebees might be in the future, we need to be putting in the right kind of data. And due to the quality of the data, we have to make certain decisions. So for the results I'm going to show you right now, we took the period 1970 to 2000 as sort of the current period of bumblebee distributions. And then we projected those at different spatial scales. So we projected onto Europe at 50-kilometer grids, because the data for some parts of Europe are not such high quality that we can't really get much finer scale than 50-kilometer grids. But for certain areas such as Benelux, we can maybe be a bit more specific in our predictions. So we tested this as well. And finally, we have to take into account the idea of thematic resolution as well. So for these first results, which I will go back to later, we use land use that is quite broadly in its thematic resolution. So we have arable, forest, grassland, permanent crops, and urban. So to answer the question, how do land use changes influence projections of bumblebee distribution under future climate change? So having a look at these two maps, which at first probably look quite similar, we can see on the left the climate-only projections of bumblebee distributions under the 3 scenarios by 2100. And on the right, what happens if we include dynamic land use alongside those. So it's quite bleak. It's still quite bleak, as in the Climate Risk Atlas. But what we can start to see is some of the difference by including this extra information about the habitat, that we see overall lower richness in the hotspots and more restricted distributions in the present for bumblebees or for the diversity of bumblebees. But we also see that once we take into account land use, we start to see extra areas of refuge that are maybe not as well captured by a climate-only model. It creates a more complex relationship with the environment. We also see that it limits into the future the northern shift of bumblebees, which fits with some of the other research, such as Kerr et al. In Science, that shows that bumblebees are maybe not so good at tracking climate at the leading edge. So we better capture that once we take into account land use. And overall, what we see at a species-specific level is that the inclusion of land use change significantly influences the predictions of range loss and range gain or range change. And that means, yeah, we're getting potentially potentially different forecasts, different futures for bumblebees, depending on what variables we include in the model. But what you might ask is, are those 6 land use classes, or 5 in this case, land use classes really that meaningful for bumblebees? Maybe for the widespread common species, but bumblebees, as we've seen, that require either heathland or natural forest edges or more specific land use requirements, our previous model is not really going to capture that very well. Land use improves our model and gives us better predictions, but are they as ecologically relevant as they could be? So the next question we really set out to answer was, what happens if we improve the thematic resolution of the land use? Can we make more meaningful models? So we fit a model for Belgium using much finer scale data, a detailed land use change model that incorporates much higher thematic resolution, as you can see here, being able to split arable areas up into certain types of crops, forest into different forest types. And what I will focus on to show here is just the grassland part, which I think summarizes quite importantly how thematic resolution and ecological relevance can affect our models in the future. If we see above the white line, above this white line, we have positive effect on this proportion of species, and below the line, a negative effect. And we see that when we do the simple low thematic resolution land use change model, we see that grassland is quite positive for a number of species. But what happens is if we split that up, we see that pasture land is generally quite negative for most bumblebee species, and semi-natural grassland is exclusively positive. And the worry here is that pasture makes up 88% of Belgian grassland land use, but we see a positive relationship when we have that aggregated together. And that's because people are not collecting bumblebees often in agricultural pastoral lands like this, grazing lands. And so we get a sort of incorrect relationship if we don't take into account thematic resolution, because we see a positive effect of pasture, but that's really driven by these semi-natural grasslands. And of course, that leads to different predictions of future distribution. So again, just having high thematic resolution versus low thematic resolution models, we see different predictions of how much range is likely to be lost by species. So we can see here that the low thematic resolution model has overall less variability. And we see that this actually depends on the species as well. So from rare to common species, we see that if we take into account high thematic resolution, we predict greater loss. And for the more common species with the high thematic resolution model, we predict less loss. But on a more positive note, having this high thematic resolution gives us much more chance that there will be a change in distribution towards increasing in range as well. It provides a more complex example of the niche. And so land use change matters, more detailed is better, but we see really species-specific responses. And so building on that, what can we use from the past to help us further improve these predictions? So I'm going to talk about a couple of studies that I was involved in, where we can see that some extra information is probably likely to, if we can include it in these predictions in the future, really improve how we can predict bumblebee distributions under climate change. These are just some examples. I won't go too much in detail in the methods, but feel free to ask questions. So in this study, which was led by Maxence Gerard of the University of Mons, we measured thousands of bumblebee queens from museum collections across a time period of 1900 to the modern day. And we see that overall size of bumblebees was increasing in time. And this was particularly common in countries like Belgium and the UK, where there has been significant landscape fragmentation across the same century time period. But we examine in finer detail. So we look really at where the species are occurring, how variable the gradient of size is in a gradient of landscape fragmentation. And we see, again, a very species-specific response. So the two larger species, Bombus lapidarius and Bombus hortorum, seem to be increasing in size along a landscape fragmentation, of course, with a lot of variability. And the two smaller species, Bombus pratorum and pascorum, seem to be decreasing in size. And we see the exact opposite relationship when we look at temperature. So the two larger species seem to be decreasing in size along a climate gradient, and the two smaller species increasing in size. So we see that size depends on landscape fragmentation and temperature. And it seems that these populations have quite a variability in this trait to be able to select for species that are larger or smaller depending on the climatic conditions, which will say a lot about, if we're modeling these species under climate change, how likely they are to have these traits that are suitable for potential future conditions. So as another case study, this one really talking about how important it probably is going to be in the future understanding species interactions. In 1889, a Belgian researcher, Julius MacLeod, visited the Guédre region of the French Pyrenees and sampled in detail the plant community while simultaneously recording all the visitors that he found on that plant community. And so we have this publication here on the left, and in 115 years later, we repeated the survey using the same methodology in the same area. And we really wanted to see how this affected the distribution shift and what was driving or potentially driving that distribution shift. So with a bit of clip art, I will show you the main results that we saw. We see overall across this 115-year period that the plant community visited by bumblebees and butterflies in both periods increased about 230 meters further uphill in their median range. Bumblebees about 130 meters further uphill on average, and butterflies about 200 meters further uphill on average. But of course, as I keep harking on about, this was very much species-specific responses. So some species, such as Bombus hertorum, showed no increase in elevation across time. Some species like Bombus soroensis increased their range both in lower and higher elevation, but overall lower increase. But some species showed really significant shifts to higher elevation, such as Bombus wafleni and Bombus gersteicheri, which both coincide strongly with a preference for the genus Aconitum. And in the case of Gersteicheri, a oligoletic relationship with the genus, so very much a dependence on that plant for its pollen resources. And they seem to be shifting in response to their host plants, is what we see in this case. And we also see that example for Asteraceae, in particular thistles as well. So some of the bumblebees that had a closer relationship with thistles, the thistles were increasing in elevation and the bumblebees also. And so this is what we see for Aconitum, how much further it increased uphill, about 400 meters on average. And so what this tells us is plants are showing very similar patterns, but potentially moving further than the bumblebees. Could this be driving the distribution of bumblebees to higher elevation to follow their feeding resources? But we also see the idea that as the common generalists move higher, they also increase the number of plant species they are feeding on at these higher elevations. So the potential for competition as well increases. We see that climate has moved uphill faster than species, so very few species were in the same climate envelope in the modern period. And we also see that there has been significant land use changes, so increased grazing at lower altitudes, and the tree line has shifted a lot uphill. So again, we have all these different factors affecting what we've seen happen over the past. And really, if we want to be predicting meaningfully into the future, we need to take into account all of this information. So to conclude, what do we need to better predict distributions of bumblebees under global change? And the first thing we show is that land use change, including it in the models, improves our forecasts, but that land use should be ecologically relevant, so applicable to bumblebee species. And really the next step with that is to try and take it a step further to look at fine-scale landscape elements and potential management to really capture what might be driving habitat suitability for bumblebees. And that means complex models of future land use change. And also, it's important that with these predictions, we're assuming that the bumblebees are in equilibrium with their environment and not taking into account the ability for species to adapt or to have plasticity in their traits, such as in heat tolerance. So I think we will see next week a good talk from the University of Mons from Baptiste Martinet, which shows that bumblebees have very different heat tolerances. And taking account that information into understanding how climate change is going to affect bumblebees may be very important, because it will, for certain species, make the climate range a lot larger, and for other species, make it potentially even smaller. And of course, species interactions. If we know that bumblebees have a strong relationship with certain plants, to model those separately or not to include that information in the model means we're going to miss some of these important biotic interactions that are driving bumblebee distributions. The same for bumblebee parasites and their host. The most important thing for Bombus rupestris is that it will have the same, it will only occur in areas where there is Bombus lapidarius, for example, and being able to take that into account in models and models in the future is very important. And this is, of course, without mentioning all the other aspects that we could be including in these models, a better understanding of dispersal, how good can bumblebees track changes in climate and land use conditions, and also aspects of demography and other aspects of evolution that look at, can they shift their phonology to different time periods instead of shifting their spatial patterns, and so on and so forth. So it becomes, if we want to make meaningful models that are useful for conservationists to create an idea of what's going to happen in the future, we really need to start be including this information, which is being captured, and a lot of people are working on this. And yeah, it just becomes a matter of adding this to our models. And of course, we see hugely species-specific responses, and so we need to model species specifically to account for their conservation needs. So thank you very much. This is a hugely collaborative work. So I want to thank all the people that helped with the work, shared bumblebees, shared their expertise, and everyone who has recorded European bumblebees, because as I said, none of this work's possible without having these records. And if there's no questions that I can't answer, please feel free to reach out to me on Twitter and I can answer them later. Thank you.
Thank you for this, I think, impressive talk with lots of information in it. We have time for a few questions, so I will look at my screen. So there's a question on from let's see, from Hernandez Castellano. The question is, altitudinal shifts are quite different for plants and bumblebees. Were you able to detect changes in species interactions?
Yes, so this is where it becomes a bit difficult. So we're sort of limited by the data that we have from 1889, and we can see for certain species where enough records were included that there are, with the specialist relationships, the visitation pattern seemed to stay the same, but of course there was a lot of variation with the majority of the bumblebees that we were working with having quite generalist patterns and shifting, and there's not really enough data to be able to say how strong that is and how much that is influencing the elevational shift, but it's probably an aspect of it.
Okay, thank you. And there's a question from Jeff Ollerton. Could the plants also be following the bumblebees?
It's a good question, but what we see is overall that I think, yeah, I always find that a difficult question. I've been asked that question a few times. And I think the question is it more likely that the bumblebees are being, is it easier for the plants to shift uphill, or is it easier for the bumblebees to shift uphill first? And what we see is that the plants in general have shown a greater shift, and that one of the reasons why the bumblebees may not be shifting as well is because of nesting resources as well. So they also have that extra added factor. But I'm not really sure, and I think yes, in certain cases, but there was very few examples of plants that had specific relationships with bumblebee pollinators in the research, and they were more generalist in what bumblebees could be visiting them. So if one of them is likely to be driving the other, I would bet on the plants driving the bumblebees, but from the data we have, we can't be sure, and so it's definitely a possibility.
Okay, so one last question by Andre Kraner. Is change in phenology of resource plants also integrated in models?
We're trying to, I think, is the best way to do that. And particularly, so even just the phenology of the bees, it becomes quite tricky to include in the models, in the sense that if we look at the adaptability of species to emerge earlier in the year to follow climatic conditions instead of moving spatially to follow climatic conditions, we need really detailed information from across the entire flying period of the species to show how that's changing over time. And there are examples of that happening, but to have enough of that data to begin to meaningfully model it, there are definitely techniques available to include temporal species distribution models, where so you look at early spring versus late spring and see how the species are likely to occur across the landscape. But for bumblebees, I still don't think for the majority of species, the ones we really want to be modeling, which are not the widespread common species, that we have enough data at the moment to include that.
Okay, thank you. So I think we now moved to our last presentation, and we